Okay, so we have begun the class. Today is the second lecture on neural language models. This is a topic in natural language processing. So, first lecture was about n-gram models. Today it's about neural language models, getting closer to the deep learning framework. So, what we covered in the last class was this important topic called n-gram models, which showed that language can be modeled probabilistically by using the simple idea of n-grams, how often certain combinations of words occur. The point of all of it was to show that it is possible to do fairly intelligent stuff by capturing probabilities. And of course, it's not the perfect model, and we need to go beyond that. But this also brings up this issue of how language can be modeled with numbers. And language consists of words and symbols, which seems like a totally different type of area than numbers, where we talk about neural networks that take numbers as input. And then we have matrix multiplications that are done with these things to get other set of values and so on. So how can language be transformed so that we can do matrix multiplications with them? And probabilities are the beginning point to show that if we can somehow keep track of words and we can associate probabilities with them, we can calculate probabilities associated with different possibilities. And so that gives you a little bit of a hint as to what's going on. But today we'll be looking at more explicitly, where we talk about how words can actually be represented by feature vectors, numbers, and we can try and make sense out of these kinds of things. So that's what neural language models is all about. So let's go further and see where we are. So the topics in NLP are n-gram models, neural language models, high dimensional outputs, combining neural language models. Neural language models are simply probabilistic models based on neural networks. And then we go on to combining neural language models with n-grams, and then we'll talk about neural machine translation. And then there's a big topic called attention models, which we'll need a full lecture for. And then there's the historical perspectives. So within the topic of neural language models, which is today's lecture, we begin by looking at word embeddings as distributed representations. So we've talked about distributed representations before, so we will kind of take a fresh look at it. What do you mean by a distributed representation? And a particular representation meant for words as a word embedding. And then we'll look at how these word embeddings can be visualized to see what is it is understanding. So this is a nice tool called TSNE. We look at that particular tool. It's based on the T distribution. That's where the T comes from. And we'll see what that method is. It's kind of similar to PCA, but it's a different objective. And then we see how words can be represented as vectors. So we start with what's called as the one hot vector, and we'll see how we can transform them into some fixed size hidden unit vector, and that's called word-to-vec. And how do we do that? How do we train a model like that? And then there are some improvements of that called GLOVE, which is an unsupervised learning of embeddings. And then we'll conclude with power of embedding. So this is all. So mostly today's lecture is about how to represent words by numbers. Okay, we'll begin. This looks like a little complicated slide, but it's a very interesting and useful slide, which differentiates between two different types of representations. Neural networks and deep learning is all about distributed representations. So something is not in one place, it is all over the place. I guess it's a bit like our class. You know, our CSA 250 was in one place earlier on, but now we're all spread all over India, it looks like. And so we have a distributed representation. So let's contrast these two approaches. In distributed representations, we extract values of hidden units. We know what input units, output units are in a neural network, and then we also know of hidden units. And those are the key. The hidden units are, we can regard them as the features. And this is illustrating features that are binary valued in this case, n binary features. And this is saying a hidden unit divides, if it's a binary valued feature, then it divides the space into a pair of half spaces. It is taking inputs from all of the inputs that it has been presented with. And if it says yes or no, it is dividing the space into two parts. So with n units, number of regions distinguished turns out to be n to the power of d. That little box gives the formula. And so with n units, we can get n to the power of d. Basically, we are saying with the order n d parameters, n is the number of hidden units, d is the dimensionality of the input. We can represent order n to the d regions in input space. So we're basically saying saying something like, if we had n hidden unit, that is 3 hidden units, and we have an input dimensionality of 2, we can get 9 regions out of it, 3 squared. And the number of parameters you need is 3 times 2 is equal to 6 parameters is what you need. And the diagram on the right side, let me see if I can point to it. This diagram here, it shows how, in this case, 3 straight lines are dividing the space into essentially 9 regions, although you can only count, I think 7 there. You can see how many regions there are. If you start at the top, there's 1, 2, 3, 4, 5, 6, 7. But this region is also can be thought of in 3 ways. Each line is dividing the space into 2 parts. So this is a case of n equal to 3. That is 3 hidden units which are set either on or off. And each of them on their own divides the space into one or the other. And together they are defining a space of 9 regions. So what we are saying is with 3 times 2 equal to 6 parameters, we are able to get 3 squared. This becomes more sensible when we have a larger number of hidden units, and we can get an exponential number of regions represented, which is the power of distributed representation. On the other hand, let's look at a straightforward symbolic representation. If we wanted to get order n to the d regions, we'd need order n to the d examples. Why is that? Is take a look at this second diagram here. This says, supposing I had these symbols given by circles, and each of them occupies some region of space. So 3 examples give you 3 regions, something like the nearest neighbor border here. And so every symbol occupies some space. So if we needed 3 regions, we need 3 samples. If we need order n to the d regions, we need order n to the d examples. In that sense, for 3 squared equal to 9 regions, we need 9 samples. For d equal to 2, that will be 18 parameters. And so it would be requiring much more parameters. And one method of representation we use is called a one-hot representation, where we say every element of a vector corresponds to a different word. If we use such a representation, then in this case, d is equal to the size of the vocabulary. Anyway, the main point is fewer parameters means fewer samples needed. On the one hand, one-hot vector representation is symbolic, and an embedded representation is distributed. So that's where we're heading towards. We're saying it's the first of these representations involving hidden units, which gives you an exponential number of possibilities with a finite number of parameters. And whereas it's not possible with a symbolic representation where things go out of hand very quickly. And we'll illustrate this point again, the next slide. So what we are after here in language modeling is to learn these embedded representations. That is the hidden unit representations. We can think of the same thing, hidden unit representation or an embedded representation. So how do we get these embedded representations is the question. And we say, well, here is a simple idea. The leftmost column here is a one-hot vector. It's a vector where every element is 0 except one of them is 1. And this could, for instance, be a 10,000 length one-hot vector. So if we have a vocabulary of 10,000 English words, we'd say, well, okay, the 17th bit corresponds to the 17th word in the dictionary. That's it. So we have converted a word into a vector, and that's called a one-hot vector. But it is an extremely large dimensional vector. And our goal is to convert them into an embedding, an embedded representation. And we, for example, have chosen here that this is going to be the embedded representation, and that consists of only 300 hidden units. So we're going from 10,000 to 300. And how do we figure out what these 300 values are? Is we have all these output units that correspond to the context in which the word is occurring. And we would have saying, you know, which context does a word, this particular 17th word occur in? Is it ant or aardvark or barber or zoo and so on? So we'd have all those 10,000 words over here, and we'd say one of these is said to be on, or maybe more than one of these is said to be on, and say it occurs in that context. So that would be the kind of training we would give it, saying for this particular word, this is the kind of context it occurs in. And so we train with enough of these samples, and eventually we learn what these hidden units correspond to, and that would be the embedding. But that's a very rough idea. We'll see a more concrete idea in the next couple of slides, which shows slightly more intelligent ones than simply giving one word at the output. So what happens here is we're starting with words in one hot vector space whose dimensionality is vocabulary size, say 10,000. And in this original space, every word is a distant square root of 2 from every other word. Isn't that interesting? That in a vector space like that, the distance between any pair, because we are talking about a 10,000 dimensional space, and so one of them is 1, the other one is 0. And so the distance between every word is square root of 2. You can figure out the Euclidean distance in that space. And what we're doing is we are going to be embedding them in a space of lower dimension. We are going from 10,000 to 300, where the distance between words is no longer a fixed square root of 2 for any pair of words. But these words are going to be nearby if they appear in a similar context. All right, that's because that's how we're training at the output. So this become intuitive. So this is going to learn which words are similar. That is a power of learning about language, is knowing which words are similar. So basically what's going on here is we are going to be embedding these words in a space. And a word embedding, W, it's a particular embedding where each word is mapped into an n-dimensional space. The Rn is the n-dimensional real space. Particular word W is mapped into a vector of n equal to, say, 200 to 300 dimensions. So some examples are given below here, that the word cat is now represented as 0.2 minus 0.4, 0.7, etc. There are going to be 200 to 300 such values, all real numbers. The word mat is 0, 0.0, 0, 0.6, minus 0.1, whatnot. It's a set of real numbers. And then once we have these, typically lookup table, it will be used for which word is that, which sequence of numbers is that. And those numbers are parameterized by a matrix data. How do we get that? This is done by matrix multiplication from the one hot vector into the embedded space. And so those values of that matrix, W theta of Wn would be a set of parameters theta n. So you can think of it as a whole bunch of numbers are the parameters for this particular embedding. So this is how we go from the world of words into the world of numbers subject to matrices. And this next example shows how a phrase now could be represented. And we have a one hot vector to embedded representation. For example, this picture shows that a one hot vector inputs correspond to ride A. All right, so we have the word ride, which is a one hot vector here for ride. And this is the word A, which is a one-hot vector for that. One-hot vector means, again, only the particular ride is one, rest of the 10,000 words are zero. Similarly, A occurs somewhere here. And from the one-hot vector, we go pick up its 300-dimensional word-to-vec representation. So we could say it's a lookup table. We have learned all these things. So that word is exactly this one, and A is exactly this one. So the input to be processed now is a neural network for some task. The word ride is this green vector of 300 dimensions. The word A is this set of red values corresponding to A, 300 dimensional. And so now we have a neural network input representation in a reasonable space, whatever be the space we can decide, and take that as input, saying what can you do with it. So this is how a word representation goes on to become a phrase representation. So what is the beauty of all of this is the word embeddings. Okay, this particular one is a word embeddings for a machine translation model. So they learned these words for a task of machine translation. And this diagram will explain that, but some task like that with an input-output relationship. And we are zooming in on areas where related words have embeddings nearby, like countries here. So look at the space here, -34 to -26, this -14 to -6. This one is 35.0 to 38.0. This is 17 to 22. The words like Germany, Iraq, Ontario, Europe, British, North, whatever, South, and so on. And then France, China, Russia, English. There is some kind of clustering going on in this two-dimensional representation. Similarly, 2003, 2004 are here. And then 1998, 1997, 1996 are here. So on. There is some kind of a clustering going on in this lower dimensional space because of the context in which they are appearing in is kind of forcing them to go close to each other. And what is this machine translation task? Is this, for instance, is about German to English. In German, you have Echt, Dicke, Kiste is the German, and we have an embedded representation for each of them. These embedded representations are being processed through a hidden network. This looks like an RNN here. This is a recurrent neural network, one word to the next word to the next word. And the final representation is being used here as what was the context in, so they can be outputting one after the other, the corresponding outputs Y, translating it into words awesome sauce in English. So this is the kind of task where these word embeddings, which is our the bottom over here, are being used, and that is a particular task being accomplished here. Now, we'll spend a little bit of time talking about what are these embedding spaces and how do you get them. This is a nice little tool that was developed by the deep learning group at Toronto for visualizing word embeddings. And the method is called TSNE, which is a technique for visualizing high dimensional data. We're talking about words being represented in 300 dimensional space. And we're saying, can we look at the 300 dimensional space? Well, we can only look at simple dimensional spaces. So like a two-dimensional space is something we can easily look at, like this one here, it's two-dimensional. And we are mapping these words, things like November, December, August, July, etc. These are all words being mapped and into this 300 dimensional space. And we are taking a viewpoint, projecting them onto a two-dimensional space and seeing how do they fall. Look at all these. In these words here, September, October, November, December are all clustered together. Saturday, Sunday, Friday, Wednesday, Monday, Thursday, Tuesday, they're all in this cluster. Him and them are in this cluster. These are all arbitrary English words. And these are like Iraq, Russia, Britain, Germany, Europe, London, Japan, China. These are all clustered over here. And then like nationalities, British, Australian, American, European, Russian, French, German, Japanese. These are all, I guess this all depends on the training set. Yeah, one of you had a question?
Sir, I have a question. Should I ask right now or should I wait?
Go ahead. Yeah, go ahead and ask me.
So, sir, you are talking about the 300 dimension space.
Mhm.
So, we get one collection of one vector for each word in 300 dimensions.
Exactly.
So,
So it
uh,
becomes a three-dimensional vector. Yeah.
is that vector norm1 vector?
Oh, is that a norm one vector you're asking? I guess that's not necessary, but it might be a convenience that we do. In the examples I've shown, they look at the values, they were like 27.5 and minus something. It doesn't look like they're all norm one. You know, they would all have been fractions of one if they're going to be
It is
norm.
not necessary for them to be norm1. Like, okay.
Yeah. You know how it is in pattern recognition and machine learning. Quite often we do that. If we do that, there are some conveniences, but that's not how we are looking at it right now. If you look at the previous slide, you see the values here and all. The values are minus 34, and this is minus 9.
So this is 2D.
This is a 2D, of course. In a multiple dimensional space, it may have a slightly different interpretation, but yeah. So we are not
Okay.
not an important point here, right?
No, I've read this somewhere because for representing a word in 300 dimensions, you only need the directions in each dimension,
Yeah.
not the uh, not
Ah,
the vector size.
not the
Because using that, you can escalate it much further.
yeah. Okay, all
Like
right.
that will give spatial difference between the two.
Yeah,
That is not required. Only the difference in directions are required to
yeah.
encode it.
All right.
Like,
Very
is
good.
that
Yeah, that
important?
very well be the case. I'm not aware of that one, but I think you brought up an interesting point there, that there is some
Okay.
advantage of making them norm one. You can normalize these things very easily. Any kind of dimensional space,
Hmm.
always normalize it by dividing appropriately and so on, right? Okay. Now let's just
Okay.
look at this. This particular representation here we just saw is a TSNE representation rather than a simple projection like PCA or something. That's not the kind of one. And this TSNE is called the TSNE stands for T-distributed stochastic neighbor embedding, and it differs from PCA or principal components analysis, and it preserves small pairwise distances, local similarities, whereas PCA preserves large pairwise distances to maximize variance. So on the left side here, it shows a PCA representation of a particular data set. And the one here, the right figure here shows a TSNE representation showing these local clusters kind of nicely separated out. It's just a more intuitive way. After all, we're just mapping onto two-dimensional space to see what is it is learning. We want to get a sense for that as an explanation, I suppose. But as the previous questioner asked me, we're going to be in a 300 dimensional space. So really the two-dimensional representation doesn't matter because that's not what we're going to be working with. That's only for us to get a window on what does this data look like. But the mechanics of TSNE, I just threw in one slide because some of you may be very familiar with pattern recognition where you learned PCA, and we can look at it here. What is this TSNE? What's the mechanics of this method? It's got a three steps actually: stage one, stage two, and a particular step after that called choosing the standard deviation. What we do here is construct in stage one, we construct a distribution over pairs xi, xj, two points, so that similar objects have high probability and dissimilar ones have low probability. And you do that by constructing a conditional probability, p of j given I is written as exponential. This is the Euclidean distance between the 2 points you can see in the numerator, and then that's again being used in the denominator. And we construct a distribution of pairs xi, xj based on the distances in the original 300 dimensional space. And in stage two, we define a low dimensional distribution. Let's say we want a 2-dimensional distribution. We construct something which is also involves exponentials. It's not exactly the same thing, but quite similar. And it doesn't have the sigmas coming into play here. And we minimize the KL divergence, this famous or infamous KL divergence, which is the which is the distance between two distributions. Between these two, between the two distributions is defined in the standard way. And we obtain the distribution, we obtain the KL divergence between the two by using a gradient descent approach of taking some value and we starting to set up the parameters for it by using gradient descent. And so that is how we choose the values for the lower dimensional distribution using gradient descent. It's a pretty sophisticated method here. And there is also a step for choosing the sigma I, which involves some binary search and using a criterion called perplexity, which is a measure that the NLP people use, which is based on entropy. And it's a smooth measure of the effective number of neighbors. Anyway, it's a non-trivial mapping, quite sophisticated mapping. So if you're curious about how do we map a high dimensional space and in a way where things that are nearby are retained in the lower dimensional space when we look at, this TSNE seems like a powerful method rather than simply trying to use PCA. So it's a newer technique introduced by the deep learning community to the pattern recognition community. Anyway, this is just a little bit of an aside. This was how do we get this kind of a map we just saw where all these words are nicely together, and TSNA helps us take such a look at it. All right then, back to neural language models. So Ngram models, a particular version of it was called class-based, which is considered more sophisticated than plain Ngrams, where we were talking about words and their distances between each other. Neural language models are able to recognize that two words are similar. So Ngram models don't have any of that. We're just calculating probability of a combination of words. And this is a little bit bringing in some semantics into play. And without using the ability to encode each word as distinct from the others. Of course, the power of the one-hot vector was every word had its own bit associated with it, so they're all distinct. And we're kind of pushing them all and compressing them into 300 bits or 300 features. And aren't we kind of losing information? Yes, we are, but it is doing it in a very intelligent way that nearby words are coming closer. And but still we have some distinction between each word at a different point in this real space there. And so a lot of effort has been put into figuring out what is a good representation, what kind of a training we have to subject it to. And you can see all kinds of word-to-vec representations. This one, nouns are being represented with co-occurrences with verbs that they are associated with. For instance, the word here, celery, is appearing with these different feature values. So one could train them saying celery occurs with each of these words, eat, taste, fill, and so on. And of course, things associated with eating and tasting may be higher probability. Or for instance, the word airplane is occurring often with ride and see and say and near, but not so much with some other things like that are occurring here. So this was actually done by someone with a trillion word text collection and trained with what context do these words appear in. And it's learning that, isn't that interesting, that it is somehow learning just by the context in which it's appearing, that airplane is associated with the riding and seeing, and whereas celery is associated with eating and tasting and so on. So this is once again a feeling for the proximity of words with other words that they co-occur with. So the strength, in this case now, when we say NLM, it's not natural language, but it is neural language model. They share statistical strength between one word and its context and other similar words and contexts. So similar words, similar context, and distributed representation, which is what we saw, allows model to treat words that have features in common similarity. So this is kind of, by going into a distributed representation, we can now have a representation where words that occur in similar contexts come together. And this also helps overcome the curse of dimensionality for sequences and handled by relating each training sentence to an exponential number of similar sentences. So we are not afraid of this exponential growth, because distributed representation we saw can create with a smaller number of parameters representations for an infinite number of possibilities or an exponential number of possibilities. Um, Importance of word embedding. Let's see. Neural networks in other domains also define embeddings. Okay. So when we say other domains, we're talking about computer vision, for example. And there again, when we go from an image and to hidden layers and so on, we saw that we do in deep learning. We are actually are defining embeddings. And so images of dogs maybe come together and so on. And embedding in NLP is more interesting than say maybe in another domain, since natural language does not originally lie in a real valued vector space. The point again being made is what I said at the very outset, that we can see very quickly how an image can be a set of numbers. These are all pixel values, 8 bits per pixel and RGB. Well, there's naturally a set of numbers you have. So what we see on a television screen or a computer monitor, we can say, well, okay, that's a set of numbers or a matrix. We can see that directly. We don't see that when we're talking about English words or whatever language words. They don't lie in a real valued vector space. They're saying these are all symbols. There are different words. Just have a list of words here. And so this kind of an embedding is very interesting, since we're mapping it into these kinds of spaces where they become numbers. So there is the mystery, the magical mapping of words into numbers. So they can now be processed the same way as an image or so many other things that are processed as numbers. Okay, I've done a little bit of a compilation of some different approaches, really about training these things. And these are called as proxy tasks, the word-to-vec training. And you see the diagram on top here, which is the proxy task for training. Like you have, okay, here you have the famous sentence, the quick brown fox jumps over the lazy dog, right? It's a English sentence where all the letters of the alphabet here. And we are training this by training examples like the word the. It appears, the pairs are the quick, the, we are training with the quick and the brown. We're putting a window of 3 over here and saying, so the occurs with quick, the occurs with brown. And so we have an input-output relationship for a supervised learning model. So the occurs with these two. Similarly, when we move the window to quick and we say quick appears with the, which is the one before, and then it appears with quick with brown and quick with fox. And similarly, the quick brown appears with the, it appears with quick, it appears with fox, and it appears with, and so on. So when we keep moving like that, and we now have an input-output relationship between the source input words, which are in blue here, and the training examples, which pairs they occur with. And now we can do a one-hot vector representation, and we got all of these words that they appear together with. So when we put a particular word over here, we have some neural network. This particular layer, the hidden layer, consists of, say, 300. And then the output layer consists of which is the right word here. We would turn on that particular one out of all the 10,000 possibilities. And that allows us to train this. So again, this is one way of training would be to pass a window over each English sentence and see which words they appear together. And we create a training set like that. And we can use TSNE to see what kind of a mapping did we get in this 300-dimensional space. We're mapping into 2-dimensional space and say, oh, wow, all kinds of similar words. I can't really see it myself clearly on the screen. You could enlarge it and take a look at it. So that was one more proxy task where we are simply moving a window to see what should be the input-output relationship. And there is a slightly more sophisticated version of this, another word-to-vec trainer, where the word W is initialized with random vectors for each word. So we have a random vector for each of them. Maybe set all of them to zeros or something. And it learns the actual vectors to perform some task. So that we saw in the previous slide some task which is predicting that these words are together, but this one is a little bit nicer, which says something about 5 grams. We learned about n grams, 2 grams, 3 grams. Okay, here is about a 5 gram thing. For example, if we have a sequence, cat sat on the mat, that's a 5 gram. That's 5 words that have occurred. And we're saying, well, can we kind of set up something where it recognizes sequences of 5? And it has to tell, the neural network is given a task to tell whether a 5 gram is valid or broken. So a valid one is cat sat on the mat. That sounds like a reasonably valid 5 gram. But when we put a random word here, let's say we took the word on and replaced it with a random word called song, and we say cat sat song the mat. Okay, that's now nonsense. Doesn't have any meaning. So it says cat sat on the mat is a good 5 gram. Cat sat song the mat is a bad 5 gram. So we now have a binary valued outputs. And so we now have a model where we have cat sat and then on the mat, this is song they put here. So we have got these word embeddings here. We started with some random values here. And then we have a model R that takes this set of values and outputs either 1 or 0. So R says W of cat, W of sat, W of on, W of the, W of mat equal to 1. Cat sat on the mat is good. Whereas cat sat song the mat is equal to 0. So this is a neural network that says whether this 5 gram is valid or not. And so we can now put in all legal 5 grams and whether they're valid or not. And we're creating a nonsensical bunch also to make sure that it learns bad stuff also, or nonsensical ones also. And using backprop, we learn all these values of W. So it seems like a pretty straightforward way of learning the embedding vectors W. And so we end up learning the parameters for W as well as R also. This is also a neural network here that is mapping these vectors into 0 or 1. But we are not so interested in R, is not as interesting as W. And the entire point of this task is to learn these vectors W, and we say that is the embedding. And now we can have a lookup table. Whenever we have the word cat, we can go look up and say, here is the value, 300-dimensional vector for W. So this is one more way of training. So there have been several attempts at training words. What kind of context do we need to get? And so we can work with these kinds of n-grams. And this particular one, based on 5 grams, how good is that? And here's a table which shows words with embeddings closest to a given word. So they have these words like France, Jesus, Xbox, Reddish, Scratched, and Megabits. And see, you see at the first column, France is close to words like Austria, Belgium, the names of countries. Jesus is similar to God, Sati, Christ, Satan, Kali, Indra, Vishnu, Ananda, Parvati, Grace. It has figured it out. Xbox is similar to Amiga, PlayStation, and all these things. These are all, I guess, video games. And then reddish is similar to greenish, bluish, pinkish. And then scratched is similar to nailed, smashed, punched. And then megabits is similar to MB per second, or bit per second, or baud, or carats, and kbit, which is kind of quite magical that we took these legal 5 grams and we trained a neural network with these representations and learned what exactly is the 300-dimensional representation for that. So there's been a lot of energy put into it. People have figured out good word embeddings, and so we can do more sophisticated stuff with them. And so the power of word embeddings is that similar words being close together allows us to generalize from one sentence to a class of similar sentences. Not just word for synonym, but switching a word for a word in similar class. Example, wall is blue to wall is red, wall is blue to ceiling is red. So it is possible to have these kinds of meaningful transformations. And well, that's not the end of story here. The word embeddings and analogies. Analogies between words are encoded in difference vectors between words. For example, the difference between man and woman. Man is a certain value, woman is a certain value. And it turns out the difference between the W of woman and W of man is turned out to be similar to W of aunt and W of uncle. Or W of woman minus man is similar to W of queen and W of king. So this is saying in this vector space, the difference is somehow meaningful. And it's saying it's not surprising since we write she is the aunt, but he is the uncle. That's the reason it is learning it. We say she is the aunt, he is the uncle. It is saying there is some relationship between she and he and aunt and uncle. And then again, word embeddings and relationship pairs. More sophisticated relationships are encoded. Relationship, for example, France goes with Paris, big with bigger, Miami with Florida, and Einstein with scientist, Sarkozy with France. I guess this isn't a very old set of words. He's still the president of France, right? I guess Berlusconi is gone. But Microsoft with Windows and Microsoft with Walmart and Japan with sushi and so on. You got all these pairs here. And these are not like the same words, but they're associated. I guess whenever they say Baltimore, they say Maryland because that's the state it's located in. Or whenever they say Dallas, people usually say Texas, like that IBM. Yeah, really? IBM with Linux, I'm not sure about that one. IBM with McNeely, no, he founded Sun Microsystems, right? Anyway, so all these are side effects. All these properties of W are side effects. We didn't try to have similar words close together. We didn't try to have analogies encoded with different vectors. All we tried to do was a simple task, whether a sentence was valid, and these properties popped out of optimization process. Neural networks learn better ways to represent data automatically. So that is the remarkable jump that's happening here. We're going from simple numbers, and it is learning things we never thought. We couldn't have thought of all these things to train it with. It has figured out these kinds of things. Now, this has been a different approach. I forget now exactly whether this was a Google effort or something. They said, well, okay, well and good. You got all these things you have done. You can train it using 5 grams. You can train it using some kind of windows being passed over these words, or some context is occurring in. And can't we make it into more of a science as what's really going on for this training purpose? And so they said, okay, let's put some effort into it. It's about correlations between words. So they came up with a method called GLOVE, which stands for Global Vectors for Word Representations. And instead of supervised learning, they use unsupervised learning. We just saw supervised learning for an input-output relationship. That's how we learn the embeddings. So this says unsupervised learning. And this they did by by obtaining global word-to-word co-occurrence statistics from a corpus. And the resulting representation showcase interesting linear structures of the word vector space. So in this space, so what they're saying is globally look at word-to-word co-occurrence statistics from a corpus. Systematically just capture the statistics instead of going about training it like you did. And by doing this, you end up with a representation where the vector differences between man and woman, king and queen, and brother and sister are roughly equal. Well, we just said that those kinds of things are going to be similar, but this thing, they got to be equal as well. So I don't have much more on this glove, but it's something to keep in mind. It seems to be a powerful method, a more recent one, maybe in the last couple of years or a year or so, which has created this glove method, and you come across this in word embedding. So nowadays, there is really no need. If you're going to be an NLP person, do you really need to start training your network from some corpus? Much of that work has already been done for you. People have looked at huge amounts of, trillion word corpus and so on, and figured out good representation. So you can say, well, there is an embedding available for me. But if you're going to be doing this on another language, let's say you want to do it Kannada or something like that, which may not have that word embeddings, or maybe there is already, you could use these methods from scratch. So the importance of word embeddings is neural networks in other domains also define embeddings. We just saw that. And embedding in NLP is more interesting since it does not originally lie in a real valued vector space. And using distributed representations is also used with probabilistic graphical modeled hidden variables. So there is other things that can be done with this, where you can construct probability distributions again. All right, so that kind of brings us to the end of 12.4.2. And
Sir, I have a doubt.
yeah, let's do that. Let's have a discussion now. Okay, go ahead. Now, is it Basil who's speaking?
Yeah.
Okay, go
So
ahead.
how do we ensure unique embedding for every word in neural network?
Well, how do we ensure? So we are not really going about saying, let us ensure that. In the input, we have a absolutely unique representation for each word, yes. So what are we doing? We are going into some kind of a real space, which is an infinite space. How many points are there in 300 dimensional Rn? That is an infinite number of points. So it is quite likely that these points are not going to be exactly the same. Unless a word occurs exactly the same way. I think therefore you can ask a question, when will two words become the same in this 300 dimensional space? When their input-output relationships are exactly the same in your corpus, then they'll end up exactly being the same, I suppose. But that is quite unlikely, right? That you will have words will have occurred with slightly different words at the other side based on the training point. So you will get something different, right? Okay.
Yeah.
Good question. Yeah.
Sir, I have one more question.
All right. Introduce yourself. Your name is Sumant Kumar, is that?
Yes, sir.
Okay, very good. Actually, what happens here is on my screen when someone speaks up, the box around it lights up. You can show your video also if you want.
Okay.
You. Oh, it's good, Sumant Kumar. Now I know who you are. That's a good idea. See, we're all figuring out this technology. So when you want to ask a question, unmute your video if you so want to do so. And so we can see. All right, go ahead, Sumant. Now what happens is when your video comes in, your name goes away. So I'd better look at your name first before your video
Okay.
comes. Okay, Sumant.
Mhm.
Yeah.
So my question was, so given this representation, can you say that two words are distinct or opposite given their representation?
Ah, okay. Well, in English, we do so many things, right? Synonyms and antonyms and things like that.
Mhm.
Slow and fast, right? Or opposite, maybe. And,
Mhm.
look at the examples we saw. Slow and fast, they probably occur kind of in similar context, this horse was fast and this horse was slow. And so they may end up being fairly close together. And there may be other
Okay.
clever things needed to say that's really opposite rather than the same. Uh, you're asking an interesting, good question about can you detect opposites or antonyms in this
Mhm.
embedded space? Okay, good question. All right, I don't know the correct answer to it. Okay, all right,
Yeah. Thank you, sir.
yeah. This is really a revolution in language processing. This kind of numbers embedded space, it is just mind-boggling. So looking at all these things, synonym, antonym, would all be so interesting. Yeah. Okay. Anyone else have another question?
Sir, I have a question.
Himanshu. All right.
Sir, this
Can
word,
you turn on your video if you want to? That is.
sir, I'll ask with only with the audio.
I don't know if you're in your pajamas or what. Okay.
And that's why.
All right. Okay. Yeah.
Two embeddings are available with 100 dimensions, 300 and 600 dimensions. So how does increasing the dimensions help?
Ah. Why would you go? How would you determine that? Okay, good. This business of being in pajamas reminded me. I saw something on Facebook or somewhere that said how to dress for these Zoom video conferences. You only have to dress the upper part of your body, because the camera is on. So you're wearing a tie and all on top, and you're in your shorts. Anyway, so dressing for Zoom. All right, then. So yeah, how does one determine whether it's 300 dimensional or 600 dimensional? Uh, this kind of gets into the computational power and what kind of discriminatory power is obtained by going to higher dimensional spaces. Something that can be kept in mind is the lessons of pattern recognition, where we talk about the curse of dimensionality. When you increase the number of dimensions, things get that much more complicated. For instance, you need a much larger training set to be able to train 600 hidden units compared to 300 hidden units. And this can go up exponentially. So there is an argument why we shouldn't arbitrarily increase it. And I guess we should learn from all the large training exercises that have been done. How did they choose 300? Why didn't they choose 400? Why did they choose 500? And maybe in a lot of language processing, you find there is a point of diminishing returns. Should we go to, in the olden days, they were just using n grams, 2 grams, 3 grams, 4 grams, 5 grams. Is it necessary to go to 6 grams, 7 grams? Again, they get extremely complicated. The number of occurrences of certain combinations is zero. So most of them are not occurring at all. So there is no value in going beyond, say, 2, 3, even 4, maybe 5 at most. So like that, is no point in going to a much larger space. So it's kind of determined by computational computational needs, as well as by the kind of returns you get by going to a larger dimensional space. Yeah, good question. Yeah. All right. Any other question? All right. Okay, if there are no more questions.
Sir, I have a doubt.
Okay, go ahead. Basil, yeah.
Yeah. So you mentioned that fast and slow will occur in the same context in one word embedding. Wouldn't that be a problem for inference when contradiction is involved?
Well, this is just a representation for the word, So we have got a representation, fast and slow, and that's all we have. So you brought up the word inference here, which is the correct one. When you're going forward to capture, what does this sentence mean? We are talking now in the context of other words to play a role. We're talking about this RNN type of structure. This is even at the earliest point of time, how do we use an RNN we're talking about? So with RNN, the context and all is kept in mind to figure out, keep in mind the RNN structure we just saw earlier on in one of the slides. The sequence of words, and then that is all condensed into the last vector, which is being input to produce the outputs. And very simple structure. So there is more than one word involved when you're trying to translate, let's say, between English and French, and there is fast and slow occurring. So all these words together are going to determine what you're going to be saying about it, let's say in German. And we're going to be looking at something more sophisticated than simply a simple vector that's passed along from the input sequence to the output sequence using what's called transformer and all that. So the word representation is just that, except the kind of representation we are giving it is kind of similar to words that are used in similar contexts. That's about it. Rather than a one hot vector, getting an embedded. But it shouldn't harm us, because we'll be using global sequence to figure out what to do with this word, right? What are you trying to do? Right? Understand the meaning, the sentiment, or the translation, and so on. Right? It's a good question. Yeah.
Sir, I have a doubt.
Okay. Now you are Shreya. Okay, Shreya from from MS Ramaya College. All right. Yeah, go ahead. Shreya, you want to turn your video on?
Yeah, sir, I'm not from MS Ramaya College.
Oh, you are. Okay, there are two Shreyas then. Okay. All right.
Yeah,
You're
yeah, yeah, yeah,
you're in ISC. Okay. All right. Yeah. Okay.
yeah. Yeah, sir. Suppose two words are like in some context, two words can be treated as a similar, but in other contexts they can be treated as like dissimilar. So how these things can be captured in a single model? Like say black and white, these two are opposite in some context, and black and white are both are colors defining some colors. So they should be in similar in some other context. I mean,
Yeah.
these things are very
Okay, good question. It relates to one of the, I think what Basil asked also, like fast and slow, he talked about. So you're asking about black and white. So we are just starting out saying, what is the basic unit of representation? So we're saying the unit is not a symbolic representation. Every word is different from every other word. That is a huge, huge expenditure on keeping every word absolutely separate in this very high dimensional space, right? And we are going into we are calling it as a 200 dimensional or 300 dimensional space as a very manageable type of space. So we're just saying black is a point in this space. White is a point in this space. Hopefully they're different because there'll be some sentences where black and white don't appear exactly the same way. So black will have a distinct representation from white. And so we now know, unless they've been mapped already into this exactly the same value, which is kind of unlikely, we just talked about. So black and white are two different points in a 300 dimensional space. And so now we have a sequence of points in this space that corresponds to a sentence. And what are you trying to do with these sentences? Are you trying to get a sentiment that it's good or bad, or what are the task is there? I guess question answering or so on. So you have to think about how it's being used. So I imagine even though they might have mapped into 2 points that are kind of near each other, one has a value, let's say 27.5, and the other one has a value 27.6, because they are going together all the time. But they are still distinct because we found at least some examples where they were not used exactly the same way. And so they are distinct. And so that information is enough for another higher level processing unit to work with them and saying, to infer from that. All right. Yeah. Okay.
So one thing I would like to add here is that, so we are getting something like this because we are doing it unstructurally.
Mm.
So since we are doing it unstructurally, the grouping happens given the data, and more often than not, black and white occur together in some ways. So we get those groupings together.
Yeah. Good explanation.
Is this one way to answer it?
Yeah. So unstructured, yeah, all of this language is unstructured. We are getting, we are taking this unstructured data. We got all these English sentences, and I showed you how you could kind of convert it to something very systematic or structured. You can say, like passing a window of 3 or 4 over all the words, and now you say which words are coming together, which words are coming together, and we are systematically training it on this unstructured data, which is kind of mapping these points and giving us the embeddings. So even though it is unstructured, we have a way of mapping them into points. Now we can look at it, quote unquote, in a structured way of these points. I guess that's another way to look at it. All right. Yeah, the word unstructured usually goes with language as opposed to a database. Database system, we have fields in a record and all that, or features, fixed set of features, feature 1, feature 2, feature 3, that's structured data. In language, we got all these things that are all coming in sequences. It's unstructured data. And we are trying to structure it in a way that the other methods, the conventional data processing, data analysis methods can be applied to them. Okay. All right, you brought in the word unstructured. Okay. All right, let's see who all. When I see your video, I don't know your name because it doesn't show that here. We have Shreya, is that right? Yeah. And Basil. Okay. Who else is on? I don't know how many students were there. I don't know how to keep track of. Okay, not bad. We have quite a few. All right. So let me go on to what we're going to do the rest of the semester. So I will continue these classes, Monday, Wednesday classes. And we have plenty of time now. That's one advantage we have. Previously, I had to compress all of it and say, okay, you go read it. Now we have plenty of time. So I'm taking my own time. If I was teaching it in the class, I would have said, I would have only been able to cover a little part of it and say, left the rest to you. So we have at least one more lecture on NLP. I still need to cover the high dimensional outputs, and that itself is interesting. And I think this NLP is a good topic, very good topic to know about. It's the most interesting one. How do you map, these symbols into numbers? And then there is this whole thing, attention models. The NLP guys have led the deep learning community lately, saying they are the ones who invented new stuff. RNN was invented by them. And now they invented this thing called attention models. And then the computer vision guys came running behind saying, wow, we could also use that. And so we'll see how the NLP guys define these things. And that can be useful back in whatever other application you might be interested in and not NLP. All right, so we'll do that. So next week's topic is 12.4.3.
Sir, I had a question.
Yeah, okay. Vinayak, go ahead.
Vinayak here.
Yeah.
Yes. Sir, you mentioned time, that's why. So because we have more time, can we extend the deadline of the GAN assignment? Because it already requires a lot of training, and most of us have still not been able to train our NLP project because we don't have the resources yet.
No problem. I don't know if any of the TAs are signed on, but I hope they heard you. I have absolutely no problem. We have the whole of April and the whole of May here. And
Yes.
so I think we've had plenty of time for project 3. I think we kind of set mid-April. Mid-April as the date, and they're also
Yeah,
trying.
project 3 is fine, just the GAN one.
The GAN one, yeah, and then you can have the rest of the time. You have half of April, and maybe let's make that May 15th. So that's a month and a half from now. And they're also setting up such that in case you don't have a very good bandwidth connection, you can use SSH on ISC servers or something like that. So I think they were setting it up. Prasanna and Lokesh, I think Lokesh was setting it up. So we are very cognizant of the fact that you might not have good connectivity, and so we'll see how we can do that, and also use the time in a good way while we're all waiting, and while we're all maybe bored. Why not spend our time like this? So we'll do that. No problem. So we will we'll set that. You send a reminder again on Piazza or something like that, and
Okay.
we'll do that. Okay, very good. I think I'll stop it at this point, and we will.
One question I had regarding the course. Are we going to have a final exam like for this course?